Hi, and welcome back to 4785, 5785. Today we're going to talk more about parsing. We're going to talk about smarter and smarter algorithms. And finally we will get to predictive parsing, which is the kind of parsing that we'll use in the compiler that we build this semester. So a big problem with parsing using breadth-first search is that grammars like the one that we talked about last time make parsing take exponential time. You wouldn't be very happy if your compiler took exponential time to compile your program. Not only do they take exponential time, but they can take exponential memory, which is even worse. So what if we find a different algorithm for searching the graph? Can we do better than the behavior of breadth-first search? Well, let's begin with an algorithm called leftmost depth-first search. The idea here is to use depth-first search, and the advantage of doing so is that it has very low memory usage. It only considers one branch at a time, and consequently on many grammars it runs very quickly. It's easy to implement. It can be written as a set of mutually recursive functions. And if you took 3011 from me, you saw this in action when we wrote a little parser that was using mutual recursive functions. It's called recursive descent parsing. So let's look at the way leftmost depth-first search works. We're parsing int plus int with this grammar shown here on the left. So we start out with the E symbol. Remember, we're doing top-down parsing, and we choose the first possible production for E, which is a T, and then we get an int, so T goes to int. Int doesn't match int plus int, so we nix that one and back up. Then we try the other possibility for T, which is paren E close paren. This also doesn't match the input, so we nix that. And then we are done with our possibilities for T, so we back up to the E, and we try T plus E, which is the other possible expansion of E. Then we go int plus E, int plus T, int plus int, and we're done. So that's much better. But remember, this is a pretty small grammar, so even though it's much better, it still has some issues. Now, one of the issues, which is worse than efficiency, is the problem of left recursive grammars. So here we have an example of a left recursive grammar, right? Because A goes to A, so the non-terminal symbol is appearing as the leftmost symbol on the right-hand side of A. And the problem with this is that if we try depth-first search, we get into an infinite loop, expanding the A over and over again. Obviously, this is a huge problem. So let's talk about this in a little more detail, with a little more precision. So a non-terminal A is said to be left recursive if and only if A goes in some number of steps to A omega for some string omega. Leftmost depth-first search may fail on left recursive grammars. Fortunately, in many cases, it's possible to eliminate left recursion. I put handout 8 on the website for you to look at because it describes how you can eliminate left recursion. And so, while depth-first search is better than breadth-first search, there's some trade-offs. So leftmost breadth-first search works on all grammars. Its worst case runtime is exponential, and its memory usage is exponential. This technique is rarely used in practice. On the other hand, leftmost depth-first search works on grammars without left recursion. Its worst case runtime is also exponential, so we haven't done much better there. But its worst case memory usage is linear, so we've done a way better there. You see this technique used often in what's called recursive descent grammars, which I described a little bit earlier. Okay, so we've got breadth first and depth first. Let's talk about another technique called predictive parsing. In predictive parsing, the leftmost depth first and best first search algorithms are modified. So those algorithms do what's called backtracking. They try to guess a production to use, and then they back up if it doesn't work. They try to match a prefix by sheer dumb luck. There's another class of parsing algorithms called predictive algorithms. Based on the remaining input, they predict without backtracking which production to use. So the idea is, instead of guessing, let's look at the next few symbols of input and try to make an intelligent choice as to what production to use. There's some trade-offs in predictive parsing. Parsers are fast. In fact, many of these algorithms can be made to run in linear time. And beyond that, they can often be made table-driven for extra speed. So not only are they linear, but the coefficients of the time complexity are very low. Predictive parsers, however, are weak. Not all grammars can be accepted by predictive parsers. So, we talked about context-free grammars, and we said these depth-first and breadth-first search algorithms can accept all context-free grammars except for the provision about left recursion. Predictive parsers can't do that. In fact, no one's really defined precisely what the class of grammars that predictive parsers can accept. But, nevertheless, predictive parsers are very fast. And so this is one of those examples of classic trade-off that you should have seen many times so far in your career here, where we trade expressiveness for speed. In other words, a less expressive grammar can be parsed more efficiently. Okay, so here's the idea of predictive grammars. They exploit look-ahead. So given just the start symbol, how do we know which productions to use to get to the input program? Well, we look ahead at the tokens that we haven't yet encountered. So when trying to decide which production to use, we look at some number of tokens of the input to help make the decision. Now, one of the issues with implementing this idea is that we have to have some number of look-ahead tokens that we have access to. If we increase the number of look-ahead tokens, then that increases the expressiveness of the grammars that we can parse. However, it complicates the parser. And conversely, if we decrease the number of look-ahead tokens, the number of grammars we can parse is decreased, but it simplifies the parser. So we need to look at some trade-offs. So try to find a happy medium. Okay, so let's look at an example of predictive parsing. Here we have the string int plus open paren int plus int close paren. We have the same grammar that we talked about before. And we start our parse here with E as usual. And then we look ahead. What's coming up? Int plus t. We use that to say, oh, well, we should use the production E goes to t plus E. Then we want to decide what to do with the t. So we look ahead again at the int and we say, oh, well, we want to make the t go to int. So we just do that immediately. Now we continue on and we're finished with the int plus t. We're finished matching the input up to int plus t, right? And so now we have that E and we have to figure out what to do with it. So we get a left paren there, and so we say, oh, well, that means that we better expand the E to a T, and furthermore, we better expand the T to open paren E close paren. Okay, so now we've consumed the open paren. Now we have an E. How are we going to parse the E? Well, this works just like it did before, right? So we have the E starts with int plus t, so we know we want to expand the E to t plus E. Okay, then we have the t, and we get int, so we know we want to expand that to int plus E. Now we've consumed the int plus plus, and we have left the int close paren, so that tells us that the E ought to go to a t, and now the t ought to go to an int, And finally, we have the closed paren, and we've parsed the whole string. Okay, that's all for this lecture. See you next time.